Okay, good afternoon. Today you are studying about the UV visible spectroscopy. So UV radiation wavelength ranges from 220 to 380 nanometer. Approximately it is 200 to 400 nanometer. Visible radiation wavelength ranges from the 380 to 780 nanometer. Approximately or generally it is taken as 400 to 800 nanometer. Usually substance can absorb varying amount of the UV visible radiation at a particular wavelength. Usually colored compounds absorb both UV and the visible region in the electromagnetic region. The substances can be taken as liquids and solids can be measured in various instruments, colorimeters, spectrometers, spectrophotometers like this. Modern instruments usually coupled with the microscopes, computers, solid substances, very small samples can also be analyzed both quantitatively and as well as the qualitatively. So before going to the visible spectroscopy, so what is color? Color is the sensation of which occurs in the when light enters to the eye. Our eye focuses on the retina, that is back of the eye. The light actually initiates a photochemical reaction in the nerve cells attached to the retina. This transmits impulses to the brains and so stimulates the sense of the color. Usually retina has the two parts, one is the cones and the rods. So cones gives the color. Usually majorly three types of the color are there. Red, blue pick up by the cones, red, blue and the green. Rods will take only grey or black and white colors. So all the colors we actually sense takes by these three colors, that is red, blue, green. It can be sensed with the only these three colors, and also rods, grey and black color can be sensed. Second part is composition of the white light. So sunlight takes white light, covers usually wavelength from the 380 to 750 nanometers. So simple physics experiment shows that the white light is actually composition of a range of the colors. So you can see in the pictures white light whenever glass prism or any water, if you take usually these 7 colors are taken place. Vibgyor, it is generally called as Vibgyor. V is violet, B is blue, G is green, yellow, orange and red. When white light falls on an object, the color detected by the eye will be depend upon the absorption and the reflection phenomena of the material of the object. So when a sample only absorbs the light of a single wavelength in the eye, majorly it absorbs if a single wavelength, the complementary sees the complementary colors. So at this wavelength is these wavelengths, the color absorbed will be this. Example violet, if color absorbed is there, we see the eye in the yellow green color. If the color absorbed is blue, we see the yellow color. If the color absorbed is green blue, we see the orange. Like this, the changes will be this absorbance and the seen by the complementary colors. This is the low wavelength and this is the high wavelength. So red, orange, yellow, green, blue and this violet. So theory behind the UV visible spectroscopy is whenever the sample gets light passes on the sample, the before light is called as the incident light. After the sample some part is absorbed, the released light can be called as the transmitted light. So by this theory, the transmittance of the light can be calculated. So incident light you can take as I naught, intensity of the transmitted light, so it can be taken as the 80. So transmittant will be 80 divided by I naught. If it is equal, then there is no absorbance or there is no transmittance. So you can see if it is 0, you can say no absorbance. Sample can absorb all or none of the incident light. Therefore, sometimes it can be absorb all the light or none. So it can be quoted as a percentage. So 100% if it is there, so percentage transmitted. So transmitted light divided by incident light into 100. So next is the part is the absorbance. So whenever the absorbance versus wavelength plotted of the A and B compounds, this can be shown like in this graph. So absorbance can be taken as minus log 10 of the transmittance. So A is equal to absorbance is equal to minus log 10. Transmittance, whatever the previous equation was there, IIT, transmitted light divided by incident light, we have taken this. Then taking minus of this log, so A is equal to log 10. So minus sign, if it is removed, it gives vice versa incident light divided by transmitted light. By plotting the absorbance wavelength, absorbance spectrum is generated. So by plotting this is the spectrum you can see here. The absorbance spectra for the same compounds A, B are shown. So here you can see both the spectrum. With the advantage of the absorbance measurement are usually linear concentration. Absorbance spectra are shown in the usually in the linear concentrations. Before going to UV, the laws are there. Some of the laws are there in the UV visible spectroscopy. Lambert's and the Beer's law. Later it combined both the scientist laws. It called as a Beer-Lambert's law. So what it states in general, Lambert's law, the sample absorbance is directly proportional to the path length of the absorbing medium. Beer's law states that when an incident light falls on the sample, the absorbance of the sample is directly proportional to the concentration of the sample. So by combining these two laws, Beer-Lambert's law, it states that absorbance of the particular sample is directly proportional to the concentration as well as the path length. So by taking this in the equation, A absorbance is equal to, this is the constant molar excitation coefficient, C concentration as well as the path length. So A is ratio, therefore A is a ratio. So it gives in the ratio, absorbance will be given in the ratio, so therefore it has no units. Molar extinction coefficient E is, or epsilon, it is called as the molar extinction coefficient. So it can be taken as 1 by molecular mole liters into centimeters. Generally it is E is equal to 1% in the 1 centimeter. So the laws of the UV visible, usually importance of the Beer-Lambert's law, usually absorbance is directly proportional to the concentration and it should be give the linear relationship in the with the absorbance and the concentration. So whenever this linear relationship takes place, we can take the calibration curve. It gives the straight line in the calibration curve. Prepare a standard. If the standards of the light to be quantified non-concentration, measure the absorbance at the specified wavelength. Prepare a calibration curve. So we have prepared here in the calibration curve. From measuring absorbance of a sample, the concentration of the light in the sample can be obtained by this calibration curve. If unknown is there, you can calculate. E can be obtained from the slope of the calibration curve. So you can see here slope of the calibration curve for a lambda max. So if the Beer-Lambert's law is obeyed, it gives the linear straight line relationship. If it is obeyed, then it gives the linear line. If it is not obeyed, sometimes deviation can also seen in the samples. So in this graph you can see the straight line, it is which obeyed the Beer-Lambert's law. These dotted lines you can see, these are the deviation from the Beer's law. So A is the positive deviation whereas B is the negative deviation. So what is A? Positive deviation. When a small change in the concentration, here X is the concentration, Y is the absorbance in the graph. So whenever small change in the X small concentration, it gives the larger difference in the absorbance. That is the positive deviation. Whenever smaller changes in the absorption, it gives the major change in the concentration. That is the negative deviation. So usually this law strictly, if it is obeys the law only with the diluted system. If the concentration increases with the particular sample, then it will not obey and it will create the deviation. So some of the rules are there for the deviation of the Beer's and law. These are the two major reasons, instrumental deviation and the physicochemical deviation. So these are the reasons. Usually in the instrumental deviations, stray radiation, if it is not, light is not proper, slit width not there, fluctuation in the single width or absence in the monochromatic light. If polychromatic light is passed, then it may be use the deviation in the Lambert's law. It will not give the calibration curve straight line, or it will not give the linear relationship with the concentration and the absorbance. Second is the physicochemical changes in the solution, usually association, dissociation, ionization and the faulty development of the colors. These may also causes the deviation in the Beer's law. These are about the laws of the UV as well as the visible spectroscopy. Next part is the ultraviolet spectroscopy theory. So ultraviolet spectroscopy concerned with the study of the absorption colorless compounds, especially ranging from the 200 to 400 nanometer. Valence electrons absorb the energy molecule, undergoes transition from the ground state to excited state. So here the electrons will absorb the energy whenever the UV light passes. Molecule undergoes transition from ground state to the excited state. So the types of molecules are, three types are there: sigma electrons, pi electrons, and the n electrons. Sigma are the single bonded compounds, saturated compounds. Pi are the unsaturated compounds, double and the triple bonds. N electrons are the non-bonded and the lone pair electrons, usually sulfur, oxygen, nitrogen like there, and the halogens. So this is the energy shifting. So energy levels, once the UV light passes, it transits sigma to sigma star, n to sigma star, pi to pi star, and the n to pi star. This is the ground state and this is the excited state. So the energy levels will be, for this it will be varied. So energy value order will be n to pi star is the least energy required for the transition state, n to sigma star, n to pi star, and the highest energy required is for the sigma to sigma star transition, because it has the saturated compound. The valence will not take very easily because of the saturation. It takes the highest energy to trans the ground state to the excited state for the sigma electrons. In especially in the pi bonds, pi to pi star, usually this transition gives rise to three type of the bands, that is B bands, that is benzenoid bands, E bands, ethylene bands, K bands, pi to pi star. Due to these systems, aromatic and heteroaromatic compounds gives the B bands, aromatic systems gives the E bands also, conjugated system gives the K bands. This is about the ultraviolet spectroscopy theory. Next, coming to the instrumentation part of the UV and the visible spectroscopy. First one is the source of the light. Second one is the wavelength selector. Here filter and monochromators are used. Third one is the sample container. Fourth one is the detectors. Fifth one is the signal recorder and the readout. We will see one by one. So next is the source of the light. This is the typical instrument outline of the instrument. This is the single beam UV or visible spectrophotometer. This is the double beam. In the single beam, only one sample can be detected. In the double beam, sample cuvette and the reference cuvette also kept. And for the focusing of the light, mirrors and the semi-transparent mirrors, motors, and the slit mirrors will be taken place. And the rotating mirror will be also beam chopper, and the rotating mirror also used in the double beam mono spectrophotometers. First is the first part is the source of the light. In the visible spectrum ranges from the usually 400 to 800 nanometer. So any lamp source which gives the adequate radiation in the particular this 400 to 800 nanometer range, which gives the adequate radiation. It should be continuous, it should be stable, and throughout the experiment. So usually the majorly used in the visible radiation are tungsten lamps and the carbon arc lamps. In the UV radiation, it ranges from the 200 to 400 nanometer. In this, usually majorly used are the hydrogen discharge lamp, deuterium lamp, xenon discharge lamp, and the mercury arc lamp. Majorly deuterium lamps are used in the UV spectrophotometer. Second part is the wavelength selector. So depending upon the particular wavelength, so you should select the wavelengths. You should convert the polychromatic light, different wavelength light, into the monochromatic one. So it should be in the single width. So for that, for conversion of the polychromatic light to the monochromatic light, monochromators and the filters are used. Usually filters are very less used. A wavelength selector that is used either absorption, construction, and the destructive interference. In this importance, filters are used. Two types of the filters are there. One is the absorption filters and the interference filters. Usually absorption filters used in the 30 to 250 nanometer range. Maximum through output is 10%. In the interference filters, 10 to 20 nanometer. Less nanometers can also taken place in the interference filter. Maximum throughput is 40%, but monochromators gives the better resolution, better stability of the light compared to the filters. So they provide continuous variation or continuous radiation in the nominal wavelength, and also it provides narrow effective bandwidths compared to filters. So construction of the monochromators involves entrance slit, collimating mirror, maybe prism, gratings, anything, diffraction gratings, focusing mirror, and the exit slits. Coming to the monochromators, there are majorly two types. One is the prisms and one is the gratings. Usually these are used for the converting a polychromatic light into the monochromatic one. Prisms are disperse light radiation. They disperse the light radiation to the colors. For example, if sunrise passes through the white light passes through the prism, it gives 7 colors. So what is the principle behind this? This is the dispersion of the light. Particular wavelength dispersion will take place. The colors will be outer. The Vibgyor colors will be given in the slit. So maybe depending upon the wavelength, the color can be separated. It is very inexpensive. Prisms, two types of the prisms are used, usually refraction type and the reflection types, usually used in the visible spectrometer. Whereas gratings are used in the UV. These are more efficient and converting polychromatic light into the monochromatic one. They give the better resolution than the prisms. Majoritarily 0.1 nanometer resolution can also be achieved in the gratings. Two types of the gratings are there: diffraction gratings and the transmission gratings. Usually gratings are nothing but rulings made upon the some materials like glass, quartz, and the alkyl halides. Usually rulings are done in the glass, quartz, alkyl halides in the gratings. Depending upon the instrument, UV, visible, IR, which instrument these are using, gratings are used. In diffraction grating mechanism is the diffraction reinforcement, whereas in the transmission gratings, refraction will take place. Reinforcement of the refraction will take place. In visible spectrophotometer, both monochromators can be used, prisms also as the gratings. But in UV, gratings are used majoritarily because of the resolution problem. In prisms, it can be only higher resolution it will give. Grating this low resolution also can be taken place. In UV, the mirrors gratings are made up of usually quartz because UV light absorbs the glass. If the UV light gratings are made in the glass, it will interrupt the sample absorbance, and we cannot calculate the sample absorbance accurately because of that gratings. Also monochromator will also absorb the glass, can also absorb the UV light. So in the UV spectrophotometer, whatever the monochromators used are made up of the quartz. This is the picture of the prism monochromator, and this is the grating, diffraction grating monochromator. Next part is the sample container. Usually cuvettes are used for the sample containing in the visible as well as the UV spectrophotometer. These are in this picture you can see this is the glass cuvette, this is the quartz cuvette. Sample volume usually 0.5 ml or less. Large volume samples 5 to 10 ml. Majoritarily the sample will be diluted. Very minute quantity is used in the UV and visible spectrophotometers. Shape of the cell. Cuvettes may be cylindrical in shape and also rectangular in the shape. Path length or thickness usually 1 centimeter it will be there. Cuvettes are thickness will be in the 1 centimeter. Material will be usually corrected fused glass are used in the visible region, visible spectrophotometer. Whereas UV region, usually glass absorbs, as I told, glass absorbs the UV radiation. So the cell made up of quartz are used as a sample containers. Fourth part is the detector. Detectors are the major part for the UV visible spectrophotometry. These are called as this UV and visible, the detectors are called as photometric detectors. And when a radiation is passed through the light radiation passed through the sample, some part of the light is absorbed by the sample. Whatever the transmitted light from the sample can be falls on the detector, and we are analyzing the transmitted light on the detector. Incident light and transmitted light we are calculating, and whatever the sample absorption we are calculating in the basis of this principle. Four types of the detectors are there. One is the barrier cell detector or barrier layer photovoltaic cell. Second one is the photo emission tube detector, photo multiplier tubes detector, photodiode array detectors. Four detectors are there. First one is the barrier layer cell. So this is the simple, cheapest, inexpensive detector. Usually it is used in the inexpensive materials like the colorimeter, fluorimeter and the nephroturbidimeter. This is the picture of the barrier cell. In this detector, it has a thin metallic layer coated silver or gold. It acts as a cathode, and also it has a metal base downside. It acts as a anode, maybe silver oxide something. The two layers, cathode layer, metal layer and the metal base layer, two layers are separated by the semiconductor layer by the selenium, because selenium has the very good electrical conductivity. So whenever light passes on the selenium layer, the electrons starting moving, electrons get mobile or moving. They taken towards the metal layer to the cathode, and it creates the potential differences between the two electrodes. So current is flown. So flow of the current depends upon the wavelength, intensity as well as the radiation of the light. This is the simple detector. Only disadvantage of the barrier layer cell is the amplification of the signal cannot be possible. Second detector is the photoemissive tubes. In this detector, you can see in this picture, this detector is composed of an evacuated glass tube. In the tube, photocathode will be there and the collector anode will be there. Photocathode is coated with the elements like usually cesium, potassium and the silver oxide, whereas anodes are coated with the silver oxide and the cesium oxide. So whenever light falls on the cathode or anode, it produces the same current proportional to the intensity of the light. The electrons gets mobile, and it gives the potential difference between the cathode and anode. It gives the flow of the current. So usually in this detector increases the selectivity of the compound. It can be used in the various range of the wavelength. The advantages, it can be used in the UV as well as the visible wavelength range. Third detector is the photo multiplier tubes. These are majoritarily used in the UV visible spectrometer. These type of the detector are most sensitive detectors, expensive also, used in the sophisticated instruments. Usually the principle employed in this detector is multiplication of the photoelectrons. In this, cathodes, anodes also there. With that, 10 dianodes will be used. So for the multiplication of the secondary emission, dianodes are used. Up to 10 dianodes are used. Because of this, it can be takes the very weak signal comparatively with the barrier layer detectors and the emissive detectors. Approximately even 200 times weaker signal can be also takes the accurate result in these detectors. In this first picture, this is the construction of the photomultiplier tube detectors. This is exactly how it looks in the instrument. These are the photomultiplier detectors. Last one is the photodiode array detectors. Operates simultaneously monitoring absorbance of solute at several different wavelengths. This is the major used in the industries. Light from the broad emission source such as deuterium light is collimated by the achromatic lens system. Whenever it falls on the holographic grating, again light will be dispersed and it passes through the diode array. So this array contains many hundred of the diodes. So through this current will be passed and the output will be regularly sampled. So the number of diodes will be more. As the number is more, it will get the exact accurate results. This is the fourth detector. Last one is the signal recorder. Last part is the recorder. So after the detector signals takes the reading, some signal recorders are used. Usually basic instruments like colorimeter, visible spectroscopy uses the digital analog. This is the colorimeter. Digital analog, it will give the signal recorder in the numbers. But whereas in the sophisticated UV spectrometer instruments, higher instruments, machineries will be attached to the computers. With the software, signal can be added. This is the UV. In this picture you can see UV with the smaller display. This is the sophisticated instrument, UV with attached with the computer. Coming to the application part, UV visible spectroscopy where it is applicable. Usually qualitative analysis of the compound. If the compound is unknown or if the compound has impurities, detection of the impurities can be taken place by this. How much impurities are there in the sample. Structure elucidation of the compound. If it is unknown compound, structure can be taken by this instrument. Quantitative analysis, detection of the molecular weight of the particular compound, determination of and dissociation constant for acids and bases. Chemical kinetics also can be calculated. Keto-enol tautorism, especially in the UV spectroscopy, it can be measured by the pi to pi star. Qualitative analysis of the pharmaceutical products. Assay of the medicinal substances can be also done. Assay of the medicinal plants, particularly whatever the extracted material is there, chemical constituent, it can be, whenever it is in the minute quantity, it can be, assay can be done. And also qualitative and the quantitative analysis of the medicinal plant chemical constituent also done with the UV and the visible spectroscopy. Some of the titrations, spectroscometric titration can be done with the UV visible spectrophotometers. Other than this, some important definitions are there. Chromophore or chromophoric group. It is a group or part in which molecular is responsible for the characteristic absorption at a wavelength are covalently unsaturated. These are the some of the groups which is responsible for the characteristic absorption at a particular wavelength. So by that absorption you can name that compound. It gives the characteristic absorption. Oxochromes, these are the saturated or unsaturated compounds. They do not have the characteristic absorption, but they can modify the chromophore groups. Example, OH group, NH2 group in the molecules. Third one is the isobaric point. It is the wavelength at which molar absorptivity of the two or similar compounds will be interconvertible. So same point, if two compounds gets at particular wavelength, two compounds get the same wavelength and same absorbance, that point is called as the isobaric point. Next is the molar extinction coefficient. E1% is equal to 1 centimeter. It means adsorption of the 1% weight by volume solution using the path length of the 1 centimeter. Lambda max, the wavelength at which maximum absorbance of a substance takes place. This is the graph of the isobaric band. Here 3 samples are taken place where exact wavelength is joined here. So all 3 compounds shows the same absorbance at a particular wavelength. So this point is called as the isobaric point. Other than that, some shifts are there. Bathochromic shift, where the lambda max towards the longer wavelength, it is also called as the red shift. It occurs due to increase in the double bond and or the triple bond of the molecules by the conjugation of the reaction. Hypsochromic shift, where the lambda max shift towards the shorter wavelength, that is called as blue shift. It occurs due to removal of the double band and the triple bond of the molecule by saturation and the dealkylation. Hyperchromic shift, hypochromic shift. Hyperchromic, increase in the intensity of the absorption of the compound. Hypochromic shift, decrease in the intensity of the absorption. Chromogenic agents and the chromogens, these are the agents which is capable of forming chromophores by chemical reactions. So these will help in the forming the chromophores. Characteristic wavelength or characteristic peak in the graph, they will form because of the chemical reaction and the ionization. This is the picture. You can see this is the electromagnetic radiation picture. So here gamma to radio waves, here longer wavelength, and this is the shorter wavelength. So near the blue shift, blue color, shorter wavelengths will be there. Red shift, longer lambda max, if it is shift to the red color side, it is the longer wavelength. So this is the bathochromic shift and this is the hypsochromic shift. Next is the Woodward-Fisher rule. In the Woodward's rule, the scientist named Robert Burns Woodward, he theoretically explained how to calculate the lambda max of a compound by the structure of that particular compound. This is the calculation part. There are several sets of the empirically derived rules are there for this, for the calculation of the lambda max, wavelength of the absorption maximum by the UV and visible spectrum. So these are the some values. by adding this base value and additional whatever the increment bonds and alkyl groups or any groups, addition of these points, lambda max points, the lambda max can be calculated. Here base value for the heteroannular dienes, usually first starting with the rules for the wavelength maximum dienes. Base value for the heteroannular diene, it is 215. Base value for the homoannular diene, it is 253. Double bond extending conjugation, these are the increments. So if double bond is present, how many double bond present? For each double bond 30 points are added. Alkyl substitute ring residues 5 points are added. Exocyclic double bonds 5 points are added. Acetate groups 0. Ether group 6 points. Thioether sulfur with ether with sulfur groups 30 points are added. Bromine chlorine 5 points are added. Secondary amines 60 points are added. This is the homoannular ring. You can see here the base value you can maybe 253 or 260. Any value can be taken. This is the heteroannular. In this 215 base value, because double bond extending from the ring to another. So here a double bond present in the same ring. So here double bond extending to another heteroannular. This is exocyclic bond because two exocyclic double bonds are there. So outer double bonds are there. So where a homoannular same ring double bonds are there, 260 nanometer is the base value. When a heteroannular different ring double bonds are there, 215 nm is the should be chosen as a base value. So lambda max can be calculated by the base value plus the substituent contributions. So here if the alkyl group 5, alkoxy group 6, RCO2 10, this 0, sulfide group 30, amino group 30. Further pi conjugations, if double bond carbon-carbon is there, that is 30. If phenyl group is there, 60. Like this, addition, substituent contribution can be added. Next is the base value for the carbonyl compound. So for carbonyl compound, 6-member ring base value 215, 5-member 202, XH halogens 208, 195, double bond extending conjugation 30. Exocyclic bonds, double bonds 5, endocyclic double bond 5, homodiene compounds 39, alkyl substituent ring residues 10, if alpha position, beta position 12, gamma or higher position 18. Like this, values can be added. For the polar groups, these are the values, OH, alpha, beta, gamma positions likewise added this. And for solvents, this is the lambda max shift. These are the sum of the values. So by example, this is the acyclic enone. So alpha alkyl group ring residues, acyclic enone. This is the enone structure. So base will be double bond towards the, this is the homoannular. So this is heteroannular. This is 215. Alpha alkyl groups ring residue. So alkyl groups will be alpha is 10, beta 2 are there. So 24. Calculated lambda max is 249 nanometer. 5-membered ring parent enone. So for 5-membered you can check here. 5-membered 202 nanometers. So 202. Beta alkyl group ring residue 2 are there. So here beta group are 2 are there. 12 into 24. Exocyclic bond 1 and 2 are there. So 1 is there exocyclic bond, double bond 5 nm. So by adding all this 230 nanometers. So this is the general 214 or 215. So heteroannular diene 215 or 214. 1, 2, 3, 4 groups are there. Alkyl substituents 4 into 5. So each in alkyl substituent 5, 20 nanometer. Exocyclic bond, 1 bond is there, 5, 214, 20 plus 5. By adding all this, 234, 239 nanometer. In this group, this is a homoannular group because inside the double bond, this is the double bond are different. Homoannular group, diene, it has 253 base value. Alkyl substituent, how many are there? 1, 2, 3, 4. 4 are there. So for each alkyl substituent, 5 nanometer. 4 into 5, that is 20. Exocyclic double bonds, 1, 2 are there. That is 5 into 2. So 10. So by adding all the absorption maximum, lambda max can be calculated by the Woodward-Fisher rule by addition of the base value 253 and the substituents 20 plus 10. So addition 283 nanometer. This is the homework for this compound. You have to calculate the lambda max, how much nanometer it gives the lambda max by adding the Woodward-Fieser rule. This is the homework for you people. Calculate the lambda max for this compound. And for more topics, subscribe to Pavitra Classes channel. Thank you.